So like we said last night, tonight we'll be looking at how to find the limit using the analytical approach. And back there you might be able to hear the guests for tonight. You guys are singing back there, so you might hear yourselves. We have a musical guest. So the first way that you can find the limit is if you have well-behaved functions or continuous functions. It's very easy to find the limit. Here's an example of one. Because you can just use direct substitution and plug in whatever value you're interested in. So let's say I want to know the limit as x approaches c from both sides. Well, I would just plug into this function, and whatever y value I get for continuous functions, no matter how close I get to c, the y value that I'm going to be approaching is going to be the value of f of c, the c value just plugged into the function. So a few quick examples. You take a look here. What's the limit as x approaches 2 of the function f of x equals 3? Well, every output is 3 for that function, so we're just going to get 3 as our y value that we're approaching as x approaches 2. And then if you look at something like the limit of f of x equals x as x approaches negative 4, well, this is just the identity function, y equals x. So the y value that we're going to approach as x approaches negative 4 is just negative 4. And now a more complicated one, y equals x squared. Well, what y value are we approaching as we get arbitrarily close to 2? We plug into the function itself, and we just get 4. So direct substitution is pretty straightforward. But what about when you have something like this? So take a look at this function. Here's the equation. It's our old friend that we were talking about the other day. It looks like a cubic, but it's a rational function, and it ends up producing a parabola-like image. Now, the reason, remember, that it produces that parabola is because this factor on the bottom actually can cancel with, if you factor the top, you can see here the x minus 1's cancel, and then you're left with the equation of a parabola. So here's the equation of the parabola. Here's the equation of this rational function, and you can see that you can take this one and put it perfectly on top of that one. These are called functions that agree at all but one point, because the only way that they differ is this rational function is undefined at that one point, and then this parabola fills in that one point for it. So it turns out that these functions are actually pretty useful for finding limits. Whenever you get a situation where you can't use direct substitution because you're going to end up dividing by 0, sometimes what you can do is you can factor the top and the bottom and cancel those factors that lead you to get undefined or indeterminate forms. Is actually when you divide 0 by 0, it's called an indeterminate form because you can't really tell what's happening at that point. And then once you've factored, you can cancel the factors, and then you can use direct substitution to plug into your new equation, and then that'll tell you what the limit is, because as you approach that c value, you end up honing in on an L value on this function, and because the two functions are the same, except at that point, you can plug into that function and see what's happening in the original function at that point. So just a quick summary on the strategy for finding limits up to this point. So first, always try to see if you can use direct substitution for a continuous function. You should be getting to the point where you can look at a function and tell me if it's going to be continuous or if it'll have asymptotes or open circles anywhere. And then if you can't evaluate it by direct substitution, then you can try to apply this theorem, find a graph that agrees at all but one point, and in the end, if you found it analytically, you can still use a graph or a table to reinforce your conclusion. If all of your techniques, the numerical, the analytical, and the graphical are all approaching the same solution, then you know that you've probably got the correct answer. Alright, so for our next example, we have a function that looks like this. The square root of x plus 1 minus 1 over x. And we want to find what the limit is as x approaches 0. Immediately you see, can't just use direct substitution because I'm going to divide by 0. So what can you do? Well, we're going to use a technique from pre-calculus called multiplying by the conjugate. And you remember the conjugate is just the sign, this negative sign between the two terms. It's turned positive. And this is a technique that we can use to get rid of radicals. So we're going to multiply by multiply our original equation by an expression that is actually equal to 1, because anything divided by itself is just 1. And when we do multiply by the conjugate, you see that the radicals disappear and something convenient happens for us because the plus 1 and the minus 1 cancel. And then we're left with x on top on the numerator and an x factor on the bottom as well. And of course those two cancel, and that was our problem originally, is that there was an x in the denominator. But if we can somehow rearrange the expression on top so that we're left with an x that we can factor out, or just left with an x by itself, then we can get rid of what was causing the problem originally. And now we've rewritten the function in a way that we can actually plug into it. And when we plug in the x value of 0 using direct substitution, we find that the function is approaching 1/2. And you could also look at the graph or use a table to reinforce your conclusion. Alright, next we're going to look at an interesting theorem called the squeeze theorem. And the squeeze theorem, we'll read it first and then discuss what it actually means. So, if h of x is less than or equal to f of x, which is less than or equal to g of x, for all x in an open interval containing c, except possibly at c itself, and if the limit as x approaches c of h of x equals L, and the limit of g of x as x approaches c also equals L, then the limit of f of x as x approaches c exists and is equal to L. So that's, again, this sort of abstract language is sometimes tricky to understand, but I think if you visualize this theorem here, then it'll make sense. So remember, the condition is that h of x is always less than or equal to f of x, and the g of x is always greater than f of x. And you can see that this function here is always above f, and then h is always below f. So this is the point here where they converge, and it looks like in this case none of them are actually defined at that point, because for the squeeze theorem it doesn't matter what actually happens at c itself, just this condition here needs to be maintained at all times. So then if we can find the limit of h of x and show that it's equal to one value L, and then we can find, hello,
Yes.
guest appearance, then we can find the limit of g of x and show it to be equal to L as well. And look here on our in our graph here, we can see that, okay, well, visually g of x's limit appears to be this value and h of x's limit appears to be this value. Now because f is always between those two, we've set up that condition in the beginning that f is always between these two functions. Therefore, the limit as x approaches c of f will also be that same point. Can think about that a little bit and see if that makes sense. Where it becomes interesting is we're going to use these two theorems to solve some limits that we wouldn't be able to solve otherwise. So these are called the special trigonometric limits, and I'd like you to memorize these so that you can apply them. So the limit as x approaches 0 of sine of x over x equals 1, and you saw that in one of your problems that you did today in class actually, and then this one too, 1 minus cosine of x over x, the limit as x approaches 0 is equal to 0, and you saw that from a table. We're going to prove these tomorrow in class. That way you understand why this is the case, but for tonight I'd just like you to memorize these two theorems so that you can apply them. Alright, so let's take a look at an application of this squeeze theorem here. So if we have something like this, the limit as x approaches 0 of tangent of x over x, then again we have the same problem. If we plug in 0, can't use direct substitution, we're going to divide by 0. But we know that the tangent can be rewritten as sine of x over cosine of x. So see if you can look over here and see what they've done. They've rewritten, here's the tangent part, there's the sine of x and here's the cosine of x, and then the x portion just shows up as 1 over x right here. So the first step is we're going to break apart this function into two different functions and kind of cleverly sneak tangent back in there with sine of x over cosine of x. The reason we want to do this is because the limit as x approaches 0 of sine of x over x is just 1. So we know that this part of the function, the limit will be 1, and then the limit of 1 over cosine of x, we can just use direct substitution, and cosine of 0 is 1, so we'll get 1 for that part of the function. So now we end up with the limits for each of these being 1, so we'll have 1 times 1 equals 1. So again, we have the same problem in example 10. We end up dividing by 0 if we just use direct substitution. So let's see what clever trick they do to actually get at what this limit is equal to. So we're going to multiply and divide by 4, but the way we're going to do it is we're going to put the multiplication by 4 on the outside of our problem here, and then the division by 4 we're going to sneak in here. So really what we've done is we've multiplied by 4 over 4. We've just cleverly placed the 4, one of the 4's outside and the other one inside. Now what that allows us to do is we end up having sine of 4x over 4x, and we can rewrite the 4x as y's, so limit as y approaches 0 of sine of y over y. And this is it. This part is in that form that we learned. It is that theorem sine of x over x as x approaches 0. So this portion equals 1, and then we're left with the 4 outside. Still, in 4 times 1 is 4. So tomorrow on the video quiz, you're going to have those exact same problems. If you need to review them, you can either watch the video again, or you can open up your books and study those examples and kind of walk through it. I encourage you to try to write out the problem and on a blank sheet of paper, and then see if you can work out all the steps on your own, and then check yourself either into the book or against the video until you're able to complete those problems that we covered today.